When we think about the climate and we're thinking about the energy of the climate, it's essentially all coming from the sun. There's no other source of energy. The amount of energy coming out of the centre of the Earth is tiny. So all the energy that's forcing the climate system is coming from the sun. So when we're thinking about what causes climate change, it's quite interesting to think about how changes in the sun, or indeed the solar radiation reaching the Earth, can affect the climate. The first thing to think about is the Earth's orbit around the sun. So that is not in a circle, it's in an ellipse. And it goes further away at some times of the year, and then nearer, and then further away again. And of course there's more solar radiation getting to the planet when the Earth's nearer in. At the moment that's happening in about January, and the furthest away is in about July. But that varies on very, very long timescales, so like about 100,000 year timescales, that very, very slowly evolves, the eccentricity of the orbit. Another factor that is responsible for the distribution of radiation over the globe is of course the tilt of the Earth's axis to the plane of the orbit. And that will result in the development of seasons. So when we have the northern hemisphere tilting in towards the sun, it's northern hemisphere summer and southern hemisphere winter, and when we have the other way round, it's southern hemisphere summer and northern hemisphere winter. So we have the amount of solar radiation distribution over the globe is varying, dependent on that. That tilt of the orbit also varies on tens of thousands of year timescale. The final and the third parameter which affects the amount of radiation getting to the Earth in terms of orbital parameters is called the precession, and that's telling us at what point on this elliptical orbit the northern hemisphere is pointing in towards the sun. At the moment, the northern hemisphere is pointing in towards the sun when it's at the furthest point in the elliptical orbit. But that parameter, that timing, also varies on tens of thousands of years. So we have these three parameters that are determining the Earth's orbit around the sun, and they will influence the amount of radiation that's coming from the sun onto the Earth, and also its distribution over the Earth. So we can see, if we look back in climate history, we will see a record of the change in solar radiation in the climate. And the most obvious example of that is the existence of ice ages. If we look at how the ice ages have occurred, they occur on approximately every 100,000 years. We're fairly sure that they're due to changes in the eccentricity of the Earth's orbit around the sun. The fact that they're not harmonic and smooth and sinusoidal as you might expect in these very slowly varying orbital changes is an interesting question, and that is almost certainly due to the release of greenhouse gases, particularly carbon dioxide, from stores in the climate system. So when the solar effect begins to warm up the climate, then that warms up stores of carbon dioxide, releases it into the atmosphere. That gives you more greenhouse effect, gives you more warming, and you get a much sharper warming than you would have had just due to the orbital variations alone. So there's a coupling here between natural carbon dioxide greenhouse effect and changes in the sun's orbit. So that's all changes in the amount of radiation that reaches the Earth due to orbital variations. The sun can be sitting there not changing at all, just pumping out its constant energy, and that's not having an effect on this particular variations. And I've been talking about variations on very long time scales. More important for consideration of current climate change is how changes in the sun itself might influence the climate. So we know that the sun's varying. You can see very clearly, don't look at the sun, but if you did, you'd see solar flares and eruptions and bright patches, and the other obvious pattern is sunspots. And we've known about those for many hundreds of years. The ancient Chinese used to observe sunspots, so that we know that the sun is not constant, that it's varying in time. And the question is whether any of these factors might actually influence the climate. The fact that there's black spots on the sun, or it gives out pulses of energy or pulses of plasma, it's not obvious how they might affect the climate. People have asked this question for hundreds of years. In fact, in the 19th century, there was a big activity called sunspottery, where there was a lot of statistical analysis of the numbers of sunspots related to various meteorological parameters. The most famous of which was by William Herschel, who was a very famous scientist, very substantial scientist. He did some work on how the price of wheat on the London Stock Exchange responded to sunspot numbers. The price of wheat obviously corresponding to supply of wheat corresponding to climate. So he was trying to do that, a very interesting question. I think the statistics of his results are not very robust. Looking a bit into time progresses, if you look in about the 1930s or so, the development of radiometers could actually measure how much radiation is coming in from the sun. So here we're trying to investigate a physical link between the energy coming in from the sun and the surface temperature. One suggestion was that when there was more sunspots on the sun, there would be less radiation coming from the sun because the black spots would be blocking out some of the radiation. Perfectly plausible hypothesis. But when they were taking these radiometers up mountains. There's a guy called Abbott in the United States going to really clean areas up mountains, trying to get long records of solar radiation, trying to relate it to sunspots. He couldn't do it, and of course he couldn't do it not because there was anything wrong with his instrumentation, but really because of the atmosphere in the way just blots out quite a small signal. Since we've had satellites, of course, we've known that solar radiation does vary, and it varies in phase with the sunspot cycle and in phase in a positive correlation. So when there's more sunspots, there's more radiation coming from the sun. When the sun is more active, it not only produces black sunspots, well, they appear black to us, but it also produces brighter areas that we can't see with the naked eye, but can be seen in various cameras. And the brighter areas, the effect of the brighter areas dominates over the effect of the darker areas, so that there's more radiation coming out of the sun when it's more active. So I've mentioned solar flares, which are very intermittent on very short time scales. Well, they vary on century time scales, but they also vary on a very well-known 11-year cycle. So you've heard of the sunspot cycle, and there's a certain amount of effort that goes into understanding whether the weather and climate vary with an 11-year cycle. Another indirect measure of solar activity is actually cosmic rays. So if you're looking at galactic cosmic rays, these are coming from well outside of our galaxy, but they're coming to the Earth all the time. The arrival outside the solar system is fairly constant, but when the sun is more active, its magnetic field strengthens and the cosmic rays are deviated. So there's an indirect relation, so that there's an inverse relationship between the number of cosmic rays and solar activity. So if we have a measure of what the cosmic rays were doing, we know what the sun was doing. And we have a measure of what the cosmic rays is doing in the cosmogenic isotopes, clues in the name, as they go back in the past. So we can look in all sorts of geological and Earth records of what carbon-14 or beryllium-10 was doing over history, and that gives us an idea of essentially what the solar magnetic field was doing, and that's an indirect measure of solar activity. So we have all these measures of solar activity on different time scales, but now we want to see actually whether these changes in the sun have any effect on the climate. One, can we detect any signals in climate that correspond to these changes in solar activity? Two, can we explain them? So it's a sort of statistical question and it's a physical question. In terms of statistics, I've talked about the cosmic ray records of longer term solar activity, and we can compare those with temperature records, proxy temperature records that we have of global temperature. And we can detect some small correlation. For a long time, there was the idea that the Little Ice Age, as it was called in the late 17th century, in which the temperatures, especially in northwest Europe, were cooler, corresponded to what was called the Maunder minimum in sunspots. So that was a time when no sunspots were observed for a period of perhaps 50 years or so. We know that it wasn't just because people weren't looking, or that they weren't trying, or they weren't seeing them, because they were measuring them before that. They were trying to see them and they couldn't see them, and then they were seeing them after that. So it was actually a depletion in sunspots occurring. So there's this sort of correlation between the Little Ice Age in temperature and the Maunder minimum in sunspot activity, and it's been a sort of trope of the whole science area that these two are linked. Actually, a new idea, which is possibly going to put a spanner in the works, is that we now understand that there was a lot more volcanic eruptions around the time of the late 17th century, and in fact it's probably the fact that there was more particulates in the air from the volcanoes causing the cooling as opposed to lesser solar activity. So actually we're getting, it's a more complicated picture than was previously understood. That being said, what about the 11-year cycle? Well, there are measures of 11-year cycle variability in a number of different climate records. The most obvious of which is up in the stratosphere, and you can see 11-year cycle in stratospheric temperature and in ozone concentrations. Nearer the surface, there are 11-year signals. It's quite difficult to extract. They're quite small and the statistics is difficult, but it does seem that there are indications, particularly in the North Atlantic region, where we seem to get colder winters when the sun is less active on the 11-year cycle. So we've got these indicators of various climate effects. Another one is Pacific Ocean temperatures in the tropics, which seem to be surprisingly cooler when the sun is more active. So if we think the statistics are correct, we now need to understand the physics of what's going on. We can understand the global temperature, surface temperature, these very, very small changes of perhaps 1 or 2 tenths of a degree in response to changes in the solar radiation, purely from radiative forcing ideas or just from energy balance ideas. But if we want to understand these more regional effects of solar activity, we need to look a bit more carefully at the physics of what's going on. One very interesting aspect is, of solar variability is that although the total radiation is changing over the 11-year cycle by perhaps a few tenths of 1%, so a very small amount, actually that's not the same at all wavelengths of the solar spectrum. So that's true in the visible, where of course most of the energy in the solar spectrum is coming in, but in ultraviolet wavelengths the variation is much larger. So if you go from say 300 to 200 nanometers wavelengths, you find that there's several % variation in solar radiation over the solar cycle, and if you go to 100 nanometers, getting further away in the UV, it's doubling between solar max and solar min. So clearly this is an interesting physics question. What happens to this UV? We've got the big changes in the UV. Where is it absorbed in the atmosphere? Well, it's absorbed in the upper atmosphere, and in particular the slightly closer UV, the 300 to 250 nanometer wavelengths, is absorbed in the stratosphere, and we can see changes in temperature in the stratosphere, we can see changes in ozone in the stratosphere, which is very interesting in its own right, but that doesn't tell us about the climate of the surface. So current work is very much focusing on coupling between the different layers of the atmosphere, the stratosphere and the lower atmosphere, the troposphere, and also coupling between the troposphere and the oceans as to how some of these apparent solar effects take place. We can now understand that changes in the stratosphere can affect the surface climate through changes in the winds and the circulations. And then there may be a knock-on effect of the wind stress on the oceans producing some of the observed ocean effects. So this is really where a lot of the current research is going on. In summary, changes in solar radiation reaching the Earth, either because of the sun's variation or because of the Earth's orbital variations, is fundamental to our understanding of climate and climate change. And we need to understand that in order to be able to be more certain about human activity and how that's affecting the climate. Very important for understanding the effect of the sun on the climate, of course, is knowing what the solar radiation is doing. And we now have satellite instruments that are flying up there, measuring the solar radiation, measuring the spectrum of solar radiation, right the way from X-ray through to the far infrared. So these measurements need to be carried out with extreme precision, and also, importantly, with a stability that allows us to know whether or not the solar radiation is varying. And these satellite experiments have been in the UV for perhaps a couple of decades, but the ones that are going into the near UV and the visible have only been going since about 2003. And the technology is not quite good enough yet, but it's being developed all the time, and it's really exciting to see how the data that they will provide will give us extra information into the future. When we have these data, we can then use them in our models of atmospheric chemistry in the stratosphere, of the climate models, and see how the temperature effects affect the upper and lower atmosphere, and how that couples to the oceans, potentially to the ocean circulations, and we can have a much better picture of how the sun affects the climate.